This is lecture number 6 for module 7 in Psychological Foundations of Musical Behavior. And today we're going to talk about perception and attention of musical stimuli, specifically how we process melody and pitch and rhythm. So the first thing that we're going to talk about, thinking about how we perceive this, we're approaching this from a cognitive perspective. So kind of our guiding question today is, how do we construct music from sound perception? How do we process the stimuli that come into from the environment? And so we're first going to talk about these different auditory phenomenon, which are really very interesting and perplexing for those of us that think that we all experience things the same way. It kind of shows that we experience things differently. So we're going to look at these auditory phenomena that have been established by a researcher named Diana Deutsch. She does research in music cognition, and so she has manipulated pitches so that when people hear them, they hear them differently. And I was talking to someone earlier today about this phenomenon, and it's kind of like how, do you remember last year, there was that internet sensation where there was a dress that for some people looked blue and black, and then for other people it looked white and gold. Well, this is essentially a very similar thing, except it's dealing with auditory sounds. And so what it is that it's called the tritone paradox. And what she did was she manipulated tones so that, because remember, pitches, especially natural pitches that we hear, there's a chroma, there's essentially which pitch class it's in. But also the information that we get from the partials, the fundamental and all the overtones, kind of lets us know in which octave that thing happens. And so what she did was she took some partials out, and then she would put in other partials in of like partner tones. And so essentially what she did was she manipulated these tones, and then it would be a tritone, and it would be a tritone either going up or a tritone going down. And the thing that's really interesting about it is people hear it differently. Some people hear it as going up, some people hear it as going down. So we're going to listen to, let me find it. So we're going to listen to, nope, that's the wrong one. We're going to listen to the tritone paradox, and then I'll explain a little bit to why we hear these things differently. Or, well, we're not exactly sure why we hear things differently, but I'll explain what it is about it that's going on. So let's listen to it. Okay, so I want you to listen to it again, and hopefully you can hear it well. And I want you to just jot down whether you think it's going up or you think it's going down. Okay, for me, it sounds like the first two are going down and the second two are going up. But it could very well be different for you. And the reason why that is that the information that, how they manipulate these pitches, it doesn't help us know what octave they're in. We can identify which pitch it is. And so, so what's going on is that it's interesting because it kind of shows that all of us are a little bit absolute pitch people. Because what she found is people are pretty systematic in what they hear. So if you listen to a whole bunch of these and they did a lot of the same ones over and over again, you would still hear certain things going down and certain patterns going down and certain patterns going up. And so since people are kind of consistent within their own ears on what's going on with this, so Deutsch, she kind of suggests that everybody has this kind of dial. So think of almost like, you remember those old telephones where you've got a dial, and every pitch of the 12 pitches are somewhere on that dial, and one of them, so let's say C is at the top of your dial. So then, next to it is C sharp and D, E, E sharp, which is F. So like it kind of goes all the way around. And for you, when you hear a C, it automatically sounds higher to you than an E or a G. It's really wild. And so the thing that's, so people, what is at the top of their dial, what they hear as the highest note, differs from person to person. So it kind of creates this interesting phenomenon where, for me, I hear that tritone paradox going up, but other people hear it going down. So she further investigated to see if there was some sort of cultural bias in this. And she really does think that there's some relation between this phenomenon and language acquisition, or even just language peculiarities within a certain region, because she did all her research in in California, and she was realizing that people that were not from California kind of had different results than people from California. So she went to the United Kingdom and continued to do some of this work, and she found that what they kind of thought was the top of their dial was different too. So this research has kind of led to some other kind of weird phenomenon as far as auditory illusions, I guess you would say. So we're going to listen to two examples of what we call pitch circularity. And what it is they manipulated the tones so that there is information missing, like the information about the chroma or the pitch class is still there, but the information about what octave it is ambiguous. And so it's hard for us to really feel like we know where that pitch is kind of in a grand scheme of pitches. So we're going to listen to this example, and it kind of sounds like a never-ending scale going down. So you're going to hear it, and it's interesting because you can tell that it's always going down, and you know that at some point it flips up, but you don't necessarily know exactly when. Or if you do have a feeling like, oh, that's kind of where it flipped back up, that might be a different place. That's, again, probably the pitch that's at the top of your dial. Let's see. So here we go. So this is going to be an internally descending scale. So again, you can hear that it's going pitch by pitch, but we never feel like there's this huge octave jump. Again, they've manipulated the sounds that we hear. Here's a version of it ascending. It's wild. I think it's just really, really, really bizarre. And so now here is another example. This time it's using a glissando. So we'll do We'll do the ascending glissando. It's really wild. It's really, really wild. Okay, so those were just kind of two interesting phenomenon that we didn't really read about in the book. The third one that we did read in the book is about the scale illusion, which had to deal with, if you remember, they put on one side, they would put kind of random notes, and they would put on the other. So, you know, they're putting in stereo on the participants' ears, and on the other side, they're putting, you know, a different pattern. But when they put it on the participant, they hear like a descending scale and an ascending scale, like, you know, do, re, mi, fa, mi, re, do, and do, ti, la, so, ti, la, do. So the brain, even though the input is coming from two different places, the brain kind of mashes them up to make them make sense. So if you read in the book, they explain it pretty well, but when you're dealing with experiments and talking about like what someone heard, it's still kind of hard to hear. So we're going to listen to that, and so you're going to hear, and I apologize that, you know, you're going to hear something in stereo that's really supposed to be from ear to ear. So the first part is the gestalt. It's both of them together. What you'll hear, a scale at the bottom going up and going down, and a scale at the top going down and going up. And then after about 10 seconds, I think, you'll hear what goes into one ear and what goes into another ear. And then when you play them together, how we mash them all up. It's crazy. Crazy, right? Our brain is kind of an amazing, amazing thing that it can just put all that stuff together. Okay, so now we're going to talk about melodic perception. So melodic perception research has been concerned with the mechanisms that give coherence to pitch relationships, and how pitch functions in attention, memory, and mental representation. One of the most basic things is auditory streaming, meaning that as you hear notes that connect to each other, that's what we kind of consider like the streaming effect helps us make that connective tissue of what a melody is. And so melodic perception is really, looking at it from a cognition standpoint, they really use the Gestalt laws of perception to help explain why we can pick out a melody the way that we do. And in the book, they do a pretty good job of kind of explaining these different laws of different Gestalt laws of perception. The first is proximity. So if you see things that are together, you kind of group them together. You know, if you have coins that are in rows that are closer, then you kind of think that those are together. You know, if there's, you know, you have two rows that are closer together of 4 coins each, you kind of think of there's 2 rows. But if there were 8 pairs that were closer together, then you would think, oh, there's 4 rows of pairs. So proximity kind of makes you think that things are grouped together because they're close together. And we'll see how that plays out in music in just a minute. The other thing is things that are similar seem to be grouped, are perceived to be grouped together. So if you see 4 4 nickels and then 4 dimes, and you're going to see the two groups of those things because they look similar to each other. Common direction is when things are moving. This kind of deals with, it has to be movement. If things are moving in the same direction, you think that's part of a group. And an example I've heard of is, if you see like a protest or a demonstration walking down a street and there's a bystander on the sidewalk, you very well may perceive that they're a part of the demonstration because they are moving in the same direction as the demonstration. Good continuation is this idea of, if there's a line and there's something that bisects it, that you still see that as one line. You don't see it as, one half of a line and another half of a line. You see it's two things that are overlaying each other as opposed to, 4 separate pieces. And then closure is where there's enough information given for you to see a whole of something, even though there's not a whole presented. And the example they give in the book is like this triangle that the vertexes aren't there, but the lines make you see a triangle. Or if you had a circle that only had part of the circle removed, you still see a circle, even though like your brain just automatically closes it for you. It's kind of crazy. So now let's chat a little bit about how this deals with music and how it helps us perceive melody. So the first thing is, even though we kind of think that melodies are based on their pitch classes, right? So even if we heard a melody where each pitch class was displaced by octaves, we could still identify it. But it's probably a little more challenging than you would think. So I'm going to play an octave scrambled melody, which you'll probably be able to guess what it is, but it may take you a minute to figure it out, while if you just heard it all and we're talking about proximity here, because when we start moving the pitch classes to different octaves, the proximity leaves. So here is the octave scrambled song. Let me find it. Here we go. Okay, so you might have been able to figure out what that was. Let's see if you can get this next one. Maybe there's not a next one. Nope, there's only one. Okay, so then here it is when they're all in the same octave. So you might have been able to get it when it was displaced by octaves, but it probably took you longer to figure it out. Maybe you had trouble figuring it out. So again, that shows that this idea of proximity, even when the pitch classes are the same, it's harder for us to process it. Okay. Along that same idea, we're going to show. There's been some research to kind of show this phenomenon by interweaving, or they call them interleaved melodies. So they put two melodies being played at the same time, but every other note is one of the melodies. So we're going to hear it, and so what this is showing is that when they're really close together, when they're in the same octave, we want to process them all as one thing, and it's very hard for us to process them as two different melodies. So we're going to listen to it one time with all the notes in the same octave, then we're going to listen to it the same songs in different octaves, and you'll be able to pick out much more easily what those tunes are. Yeah, I think the second one is much harder than the first one. Okay, so there were 4 songs in all of that. Did you get them all? Did you get all 4 of them? All right, so now we're going to listen to those 4 songs. They're being played. They're still interleaved or woven together, but this time they are an octave apart. Did you get them? Okay. So yeah, so that kind of shows when they're together, we really process them as one thing. But if we move them apart, if they're not as close together, then we hear them as 2 distinct things. You might say, well, why is this, like, what's the practical version of this? Well, it's used all the time in music, right? So you may recognize this, maybe not. So Bach does that exact thing, is that when he does this fugue where the tonal information is very, very similar, he moves them away from each other so that you can process what's important and what is, the main information he wants you to hear. Okay, so similarly, people have, in addition to proximity, by using these interwoven melodies, they have done it with they've shown that similarity also affects how you process melodies. And so again, those same tunes, this time the melodies are being played by different timbres. So see if you can still pick them out with the different timbres. Those timbres are kind of... So the thing that's interesting there is that it's within the same octave, but it's a little easier to pick it out because they have dissimilar timbres. Same thing with different amplitudes, so that if one is louder than the other, then it's easier to register them together or to process the 2 different things simultaneously. Okay, so one thing that research has looked at how we process melodies is that we process contour and interval perception. So we perceive contours and intervals a little. It's a lot easier for us to process contour than necessarily to process individual interval. And just to make sure, when we're talking about contour, we're talking about the shape of the melody and pitch height. And so contour, as I just said, contour changes are more easily perceived than interval changes. And then an interval is the distance between 2 adjacent pitches. And so if something has the same, and you guys know this as music teachers, right? If someone plays essentially the same contour, but they just miss a note, especially if it's in the same key, it might be a little harder to notice that they're not playing the right note. So we're going to listen to 2 examples from the MBEA, which we've talked before where these are used to identify people that can't process music. And so you're going to hear two things, and you need to decide whether they're the same, whether there was a contour difference, or whether there was an interval difference. If something was wrong based on an interval, or something was wrong based on a contour. Okay, so there'll be three. All right, so you should have gotten that the first one was a contour change, the second one was an interval change, and the third was the same. Now we're going to listen to three more examples, but this time they're in different keys. So you still need to decide whether they're the same pattern, whether there's a contour change in the pattern, or whether there's an interval change in the pattern. But the first one and the second one will be in different keys. So for those three, the differences were the first one was an interval change, the second one they were the same, and the third it was a contour change. Okay, we're going to talk about tonal hierarchy and just in just a little bit. We'll come back to that in a little bit. We're gonna change gears now and talk about how we process time perception a little bit. And one thing that was kind of brought up in the text is that if you ask people just to tap a beat, like maintain a steady beat, have a spontaneous tempo, that most people kind of gravitate to a tempo around 80 beats per minute. I'm sorry, 100 beats per minute. And as it said in the book, that we really don't know why we do this. It doesn't seem to be connected to heartbeat. It seems to be connected to walking speeds. I mean, I don't think they think that that's why it is. They just notice that other things that are close to 100 beats per minute is walking speed. It could be that tempo is a tempo that is easy for us to entrain, to have entrainment on certain physical activities, and so like walking. So maybe that's why we have the spontaneous tempo. And so, okay, we're going to talk about not only just tempo, but we're going to talk about rhythm, tempo, and meter, and how all those things are perceived. And so you guys probably know all this, but we're just going to really clarify for those of you that may not be as familiar with the musical world. But, how do we define rhythm? Rhythm is one of these things that, especially music teachers, we know what we mean when we talk about we need to work on rhythm. But to come up with a definition, it's a little harder than you might expect. So if you ask what is rhythm, Jelly Roll Morton, he said, if you have to ask, you ain't got it. So for music cognition, though, we have a couple of different definitions we can use. Rhythm can be a set of time spans that elapse between note onsets, or Another definition is a serial figure based on the arrangement of discrete time intervals. So, the things that we have to remember about rhythm is rhythms are the patterns of the onsets, and that rhythm is about the relationship to each other and to the underlying beat. And so in rhythm perception, we have a couple of things to think about. One is that rhythm patterns sound the same regardless of the speed at which they are presented. So that's kind of a little misleading. So it's meaning that the relationship doesn't change. So if a note gets half the beat at a fast tempo, then it gets half the beat at a slow tempo too. So rhythm perception is based on the relative relationships or ratios between duration values, much in the way pitch perception functions. And so, if you had dotted quarters followed by a dotted quarter followed by a eighth note and then two quarter notes, that would sound exactly the same as a dotted half followed by a quarter note and followed by two half notes. What is on the page does not mean that we're going to perceive it any differently. It's about the relationships between the pitches. And the thing that's good about the human brain, again, is that we have this categorical perception of rhythm, and that we tend to group rhythms regularly in the face of certain time inconsistencies. And what that means is that, yes, when, if people don't get right on the beat, we can still hear it as being on the beat. Or we can kind of put it in the category of, okay, it's supposed to be on the and. We don't, it doesn't affect us to think that we don't think that it's irregular. And then when there are rhythmic irregularities, it really kind of makes us very aware of what the rhythm is doing at that moment. There's two different theories of, and again, these are theories. They're not necessarily, there is some empirical evidence on both of these things to kind of suggest that this is what is going on in our cognition to process rhythm. But, this is still a very new field. So one is the dynamic attending theory, and the other one is the generative theory of tonal music. And so in dynamic attending theory, what happens is that in listening to music, we tend to induce a regular beat at a particular level. So we hear music and then we fix a beat to it, which again, for most people, is kind of around that spontaneous tempo. And that beat is stable even when events happen at other places in the music. So that means that, even if there are subdivisions going on, that's not going to change it. Or if we go to larger note values, we'll still feel that underlying beat. That we can adapt to violations of beat expectancy over time. So if something happens that, kind of is a little hiccup, well, after, kind of being conditioned to it, we will not see that as a violation of time. Multiple related oscillations are activated by multiple time levels and will bind over time. So that's essentially saying that we hear that beat across different hierarchies. So we can feel the beginning of the beat, beginning of the measure, we can feel, section, we can kind of create those boundaries of where how the meter is pulling the structure together. So we're going to listen to 3 examples, and I just want you to close your eyes and tap along with each piece.
I need somebody help, not just anybody help. I need someone help. much younger than today. I never needed anybody's help in any way.
Second example.
Yesterday, all my troubles seem so far away. Now it looks as though they're here to stay. Oh, I believe in yesterday. Suddenly, I'm not half the man I used to be. There's a shadow hanging over me.
Okay, sorry, I didn't fade that out. All right, and here's a third example. Close your eyes. Listen.
Ah, look at all the lonely people. Ah, look at all the lonely people. Eleanor Rigby picks up the rice in the church where a wedding has been. Lives in a dream, waits at the window.
Okay, so the fact that this is an online class, you guys can't necessarily feel. Some of you might have had different beats that you were tapping to. For instance, for yesterday, you might have had yesterday. That could have been your tempo, or maybe you had yesterday. So how you perceive it is your own internalized version of the rhythm. And so a couple of things influence how you group what you heard as being kind of the underlying beat. One, the speed of the music can really influence the most readily perceived level of rhythmic organization. This has been demonstrated through studies of synchronizing to various rhythmic levels. Also, the activity that's going on in the music, like for instance, the Eleanor Rigby. I think it would be really hard not to hear that gunk, 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 gunk of the violin playing. So tempo and what's going on, but also experience seems to play a role in how people process the underlying rhythmic beat of the music. More experienced listeners begin tapping at hierarchical levels and have access to more levels within a given piece. So meaning kind of like going to that yesterday, if you've got that yesterday. Okay, so if you had that, then that's that may be because you are more experienced in music, and so you have that, you know, that's that, you know, not every beat needs an accent on it. So, okay, so kind of going along with tempo and perception, what role does tempo play in time perception? We have this phenomenon about tempo speed limit. And what that refers to is that there are certain thresholds that if we go beyond, it's really hard for us to process them. So the upper threshold, if we have tempos that are faster than 600 beats per minute, it's really hard for us to process the individual beat. What tends to happen when you go faster than a certain threshold, you then kind of go into double time, and you hear a macro beat as now being the beat. Same way that we have an upper threshold, we have a lower threshold, and that's 30 beats per minute. If you have something that's 30 beats, which is really slow, right? If those of you who conducted, if you have anything that's like even 50 is really hard to conduct. So if something is 30 beats per minute and that's the pulse, it's really hard to really feel like you know the regularity of when that beat is happening. We can't process it as well. So the typical range that we kind of process things in is between 50 and 140 beats per minute. And so if things go below that, then we start trying to feel like we start feeling the subdivision as being the beat. And if it goes above that, then we start doubling down. So we start hearing the half note as being, if the quarter notes go to, 200 beats per minute, then we hear the half note as being the consistent beat. All right, so we're now going to go back and talk about tonal hierarchy just a little bit. And so in the book, it talks about the tonal hierarchy concept, and that's where the pitches within the scale, some pitches within the scale are not viewed as being as important as other pitches. And you'll remember in the book, there's like this really ornate diagram of like a cone, and then you've got, you have do at the apex of it, and then you have mi and so, and then re, fa, la, ti, and then you have all the accidentals on the bottom. So how they went about and figured out this theory is that what they did was they played these prone tobe tests. That's not right. Tone probe test. There we go. And so they played a scale. I'll play an example in just a minute. They played a scale, do, ti, la, so, no, no, and then they would play another random note. And then the participants would then say if it fit or not. And so let's listen to the examples. Here we go. Kind of hard to hear. That was a flute sound. Okay, it's hard to hear them. But anyway, so the results are kind of what you expect. So when they did this experiment with lots and lots of people, when that missing note was do, it got high agreement that yes, this fits. When it was so, there was some people said yeah, it fits. But then for me, a little less, fewer people said that fit. But then pretty much everything else was kind of pretty low. So it's kind of like there's this idea that these things fit. And they did these tone probe tests that weren't just scales. They also did, does this fit the melody? Does this, and so there's definitely this concept that within music listeners, they definitely expect to hear a certain note to fulfill it, to fill in the gap of whatever was happening. So, yeah, I'm looking at different graphs. Yeah, so essentially it's just, it just shows that that most listeners, even non-musicians, they know, and you know this too, right? Like if one of your kids play an accidental that, is not the right note, like they know it's the wrong note. Even their parents know it's the wrong note. So it's, it's definitely, it's all about, does it fit within the scale structure? So the tonal hierarchy theory is that Do is at the top. It gets the biggest, it's definitely the most important note to the scale, then mi and so, then re, fa, la, ti, and then all the accidentals, right? So let's talk a little bit about the cognition of musical structure. And so this is the third chapter that you read for this week, and I'm not going to go into a lot of detail in it, just because it's really an introduction to these theories, which I don't necessarily think are super important for this class, but it's just good for you to know about what they are and kind of the big idea behind them. So we're going to talk about the generative theory of tonal music, GTTM, and then the implication realization model, the IR. So the generative theory of tonal music is really based on Gestalt laws of perception, what we talked about earlier: similarity, proximity, good continuation, closure. And it's also based on some of Chomsky's linguistics theory, which again, I'm not totally, I don't necessarily understand that component of this a whole lot, but it's, in addition to those two things, it's also related to Schenkerian analysis, which I don't know if you guys have had. Some of you might have taken Schenkerian analysis as your theory elective, but essentially what Schenkerian analysis does, and it briefly talks about this in the book, is you kind of, you go from Roman numeral analysis, and then you look at the functions of what the chords are doing, and you try to simplify everything. And essentially, Schenkerian analysis is all about going from 5 to 1. You're always going from, a feeling of unrest to a feeling of rest. You want to end up on a tonic chord. And so they make a distinction in the book, which I think is really important, and that Schenkerian analysis is an aesthetic theory. It's trying to explain why some things are, more aesthetically pleasing than others. And then what GTTM is that it is a theory on how we process musical structure as it unfolds over time. And so that's kind of the next point on this, is that GTTM looks at what is the relationship of the heard structure, which is actually the auditory stimulus you have, to the musical surface, which is what the listener, what they think of the entire structure. Again, this is all kind of, in some ways, we're forging into philosophy here, because it's, what is the musical experience? Is it what you experience in the moment, or is it the experience you have over time from when you start listening to a piece? I don't know. Anyway, so sorry, that was a random tangent. Anyway, so what they were trying to do with the GTTM, Lerdahl and Jackendorf, they were trying to put forth a testable musical grammar with 4 components and rules that govern the cognitive structure of rhythmic and melodic elements in music. And so, those four components that they were looking at were grouping structure, metrical structure, time span reduction, and prolongation reduction. We're only going to talk about grouping structure and metrical structure right now. You can go back and read in the book what it says about time span and prolongation. But within GTTM, there are 2 types of rules. There's well-formedness rules, and there's preference rules. And the way to think about it is that well-formedness rules are rules that, yes, this is what should be done. Like, this is how we should do it. And then preferences, well, we sometimes do it this way, or we mostly do it this way, but not all the time. So well-formedness is more, is is more consistent, and it's more likely to be something that you see over. It's part of the bedrock of understanding of music. While preference is, well, most of the time melodies go this way, or most of the time we structure things this way, but not always. So we'll kind of get into a little bit of what those types of rules are now. So when looking at grouping, so grouping structure is how we assign group boundaries to a piece in a hierarchical fashion at every level. So a well-formedness rule right, that's what I was just saying. So well-formedness rule for grouping is boundaries may encompass but not overlap. So when you think about phrase boundaries, you can't have a phrase that goes into the middle of another phrase. That doesn't make sense. In the same way, you can't have phrases and then you have an A section that goes into the middle of a phrase. Like, that doesn't make any sense either. So boundaries can encompass. So, a section could contain two phrases, but it can't overlap grouping structures. Also, the grouping process is the same at all hierarchical levels. Again, that kind of goes with what we're saying, that if there's an ending somewhere, then that's going to be an ending at all the higher levels above it. Now, preference rules, again, this kind of goes to what I was saying. The well-formedness rules is like, this is more universal. We do this almost all of the time. And then preference rules is, well, we do it most of the time, but maybe not as much as we do these other rules. So, so the preference rules for grouping structure are things like parallelism. So, especially when you look at, music of the classical era or even of the common era, they like parallel structures where they're roughly the same length, question-answer kind of structures. They're normally symmetrical in that, same number of measures, same number of beats, that kind of thing. You might also have articulation of boundaries, so you might have musical devices that kind of say, this is the end of the boundary, or this is where the boundary of the grouping structure is. It may be a rhythmic device, it may be a fermata, it may be, that's, so those are preference rules for grouping structure. For meter perception in GTTM, the well-formedness rules are a beat at any level must be a beat at all the smaller levels, okay? So that makes sense, right? If you're feeling like, if you're feeling that was the tempo in yesterday, but if I start subdividing it, you should still be able to hear that other tempo. Another well-formedness rule is that there's equal spacing of beats, and that the subdivisions are either duple or triple. And that pretty much, that happens at, in all Western music, essentially. So let's hear an example of well-formedness rules, and you'll see the first example, this is abiding by the well-formedness rules, where the beats, even though the note values may change, the beat is still aligned. Okay? Here is an example where the beats don't align. So it's a little more haphazard. I mean, the first two measures kind of sound like something that you would hear now all the time in kind of, 20th century music, but as far as these rules go, it doesn't. The beats don't align. Preference rules for meter perception is that there are cues for strong beats, including the cues for strong beats include attacks, accents, change of dynamic, register of pitch, harmonic change, and suspensions. And then parallel metrical structures apply to parallel grouping structures. So that makes sense. Oh no. I just totally lost where I was in my notes. One second, I'm almost there. Okay. Oh yeah, so in meter perception they have three types of accents. Phenomenal accents, which include length of note, dynamics, register, timbre; structural accents, which are the points of arrival and departure resulting from tonal influences; and then metrical accents that are accented because of where they are within the measure. So yeah, I think those are mentioned in the book. Yeah. So if you want to, do a little more research on that theory, feel free to. Let's talk just a little bit about implication realization model in our few minutes remaining. So the IR model is really based on this idea that there are expectations of, well, the biggest thing is that the difference between the idealization realization, I always get the implication realization model that's different from GTTM. The GTTM is that it's this cognitive response to the musical surface, like what is happening right now. And the IR model is more of a kind of the process of expectation as you listen in time to a piece of music. And so there's this combination of expectations. One, from bottom-up processes, which are also called dynamic expectancies, which they say are kind of subconscious and things that kind of going along with probably some of those things we were just talking about how rhythm should be, how things are structured and how rhythm should fit together, that sort of thing. Things that you don't necessarily think about, that kind of puts the structure of music together. But then there are also top-down processes, which are also called schematic expectancies. And that's where you, based on your experience of what music should sound like, you are able to process what's going on. And so if something is, if you have a deceptive cadence, for instance, you would you'd say, oh, that's a deceptive cadence. It's a chord that goes out of the way that you weren't expecting. But then you're like, oh, even though that wasn't expected, it does fit in with what I already know about music, and that's, oh, we'll probably have an additional phrase now that will conclude the entire piece. So in the book they talk about this model, and they go through all of these different these different examples of rules or things that happen, similarity and differentiation. They go through intervallic difference, registral direction, registral return, proximity, closure. They explain in all these little rules in the book. I only know these things because I reread them, and I don't know that they're necessarily super important unless you're planning to do some research on this type of theory. But the thing that's interesting is when you look at those rules, they are kind of the rules that you learn in theory. So, right, think it's registral direction, or intervallic difference. You normally, if you have a small step, then you're going to continue in that direction. But if you have a big step, then you're going to go in the opposite direction. Like I remember 20 years ago in my theory class, my theory 1 teacher talking about that and writing a good melody. And I don't think she based it off of this theory. She just said, oh, this is how you write a melody. And so some of this is, it would be interesting to see where the genesis of all this comes from. This idea of registral return. If you make a large leap, then you're going to make your way back to where you started. And there's been research in both of these, GTTM and the IR model, that kind of suggests that there are things about this that are good or that work. And then there's also research that shows, well, this doesn't necessarily work. I mean, I think one of the things that these researchers really want is to show that this is a way that humans process musical structure. But what they're finding is really, well, these are ways that people in Western culture process Western music. I think there's still some voices out there that are saying that this doesn't necessarily work cross-culturally. So, and we've already talked about that a little bit in the chapter on music from cross cultures. And with that, we end our lecture for the week. All right, have a good one. See you later.